Welcome back, everybody, to day 17, 18, 18, 18 of Foundations of Programming. We are going to pick up from where we left off yesterday. We were talking about Big O and common problem-solving patterns. I believe we talked about two. It was the frequency counter, and we talked about multiple pointers. Um, we cut off a little bit short yesterday, but today we're going to pick off from where we left off. Let me go ahead and get my screen shared. I believe we had covered multiple pointers. We then went into unique values. Did we complete unique values? I actually don't remember.
We didn't.
We did not. That's right. Yeah, unique values is gonna be the next one. Let's take a look at it. There should be another multiple pointers example. We should all be looking at VS Code right now. We're gonna start off right off the bat, working on the assignments. We're going to write a function called count unique values, which accepts a sorted list, right? Sorted. And it counts the unique values in the list, right? There can be negative or positive numbers in the list, but it will always be sorted. Here we have an example. And also, this sounds like it'd probably be easier to do this with a dictionary. But we have a list here, right? It's a sorted list. And it's only has two numbers, right? So the output of this ends up being two, because one, although it appears 5 times, we're only going to count it for its one appearance, and everything else is irrelevant, right? And then two appears once as well. So there's at least two unique numbers in here, whereas the rest is duplicates. The next one we get a return of 7, because 1, 2, 3 appear once. 4 appears 3 times, but we obviously only encountered its first occurrence. So that's 4 unique values. We then get to 7. It appears twice, but we only count 1. That's 5. Then we count 6 for 12, and then 7 for 13. Right? Pretty straightforward. Now, attempt to do this with a multiple pointers, because this should be a multiple pointers assignment. But if you can't do it multiple pointers, then you can use a dictionary if you like, but try multiple pointers. I'm pretty sure you can do it with multiple pointers. Now, when it comes to the algorithms that we're working on, the goal is not to, I guess, solve the question, because more likely you could probably solve the question, right? The goal is to take this algorithm and implement it into the question, right? So you learn how to implement it. Make sense? So like, what if Tim's like really good with dictionaries? He could probably like get away with solving a bunch of answers with dictionaries, but the point is to train all the other different types of methods, and then you essentially become more versatile in different problems. Right. So attempt to do this with the multiple pointers technique. We'll take about 10 minutes with this, so we can move on with today's lecture. Yeah. Okay. We'll take a small little pause to ensure that we're all on the same page. So we are working with some common problem solving patterns, Kenny. Right. And one of the patterns that we talked about yesterday was using what we call the multiple pointers pattern. Right. The way that this works is that you get some kind of list, and then you assign 2 pointers. Right. This could be a start and an end pointer, or it could be start in the middle, or they can both start at the beginning. But the point of having 2 pointers is to be able to uh, move around a variable throughout your list, right? For example, and I use a TL draw one for example. Uh, this is from all the classes we've been doing. right? If you had this list, what we do is we create two variables. We'll call it start, or we'll say pointer one. Pointer one is equal to 0, and pointer two is equal to, let's say, 1. What this is going to do is the values that are assigned to these pointers represent the indexes in our list, right? And the reason why we do two pointers, it usually because you're trying to check combinations from what I've seen, right? Let's say the problem in question here is find the greatest sum of two numbers, right? So I have to find the two numbers within this list that when added together, they are the greatest sum compared to any other combination. So what needs to happen is I need to be able to grab one index, let's say index 1, and then see what is the sum of 1 plus 6, or the sum of 1 plus 2, 1 plus 7, 1 plus 3, 1 plus 5, and so on and so forth. See which one was the highest, right? And then after I check every possible combination with 1 and the other numbers, I'm going to go ahead and shift to the next number, which is going to be 6, and check every possible sum combination with the number 6. So these pointers allow us to do that. Pointer 1 will point towards the initial number that I want to check every possible combination with. And pointer 2 would let me switch over the combos. So for example, I would get whatever the index 0 of nums and index 1 of nums, add them together. And then I will save the sum to some temporary value. Afterwards, I will increase the value of pointer 2 by 1. So now I have access to the 1 and the 2. And then I will once again add these up, compare the sum, and then I will shift pointer 2 again. And pointer 2 will be incremented until I reach the end of this list. Once I've encountered every possible combination here, what's going to happen is I'm going to increase the count of pointer 1 to index 1, right? It went from 0 to 1. Because I already found everything for the first number here. Now I'm going to go to the next number. And then pointer 2 is going to reset. I already have the combination of 1 plus 6, right? So I don't need to go all the way to the back. I'm going to start wherever pointer 1 is at and then increase the count by 1. So 6 and 2, 6 and 7, 6 and 3, and then 6 and 5. Once pointer 2 iterates for everything, I increase the count of pointer 1. And I'll repeat that process. 2 plus 7, 2 plus 3, 2 plus 5. And I do that until pointer 1 completes a full iteration through this list. Right? That's how we can utilize two different pointers, right? Or essentially variables that point to specific parts of our list to find possible combinations, right? Does this make sense to you, Kenny? Okay. All right. So that's kind of what we're doing here. Now, the unique values assignment, I want you to implement that same logic of having two pointers to find the unique values in here. Now, a way that we can do that, and we can break it down. Let's say I have this list 1, 1, 1, 2, 3, 3, 3, 3, 4. There's 4 unique values in here, right? But technically there is like 4, 5, 6, 7, 8. There's 9 numbers in here. 9 numbers, but 4 of them are unique, right? If I wanted to find the unique value for this specific list, what I might do is I'll get P1, once again, is 0. P2 is 1. And let me put these in their own text block so I can move them around. I'd probably start like this. I start in the beginning. I won't use a start and end pointer. I will put both of these at the very beginning. What I would do when I first start is I will compare my pointer 1 and pointer 2 to see if they're equal to themselves or not. If they're not equal, I would create some kind of variable. Unique counter is equal to 0, right? It'll start at 0, something like this. Or probably start it at 1, because at a minimum, you should have at least one unique value if it's not empty, right? Something like that. But you get what I'm trying to say. I would compare these two. I would say, hey, is P1 and P2 equal to each other? If they are, then my unique counter stays at 1. If they're not equal to each other, I would increase the counter by 1, which therefore I've encountered two unique values. But in this situation, I've only encountered the number itself 1, and they're duplicates. So I've only encountered one unique value. Then I should increase P2. And I'm going to keep increasing P2, right, until it is not 1. Well, because I know this is sorting, right? What did the problem say? Sorting, right? Except a sorted list. So I know if they're not equal to each other, more than likely, if this is 1, the next one's going to be 2 or something higher, right? So when I come here, because they're equal to each other, I'm going to keep P1 at 0, and I'm going to keep moving P2 until I find something that is not the same as 1, until I find a unique value. When that happens, I'm going to increase my unique counter by 1, and then I'm going to change P1 to the most recent one. And then I will navigate P2 to the next one. I'll see that these are different. They're both unique. I increase my counter on my unique counter variable, shift P1 to the side. And so on and so forth. Do we see how we can use multiple pointers on this now? Silence is compliance. All right, let's get it. Time is 5:43. Let's give it 10 minutes. So let's come back at 5:53. Start the recording. Does anybody want to volunteer and show us their code at all?
Um,
It
I,
was
I did I did a little differently than than the pseudocode you were kind of lecturing us, but I mean I still did it a multiple pointers way. It's just a little different.
That's fine. Let's see it. The
Okay.
reason why I recommend you guys always volunteer is because if I do it, I'm gonna talk a lot more. It's gonna take us longer.
Okay, the first thing is if the length of the list is 0 or the length of the list is less than 2, just simply return the length of the list. So that basically covers no values or just one value. And then pretty much get into the nitty-gritty where left is 0, right is 1, which pretty much represents the index and result. Or I should say the unique value is already set to 1 because if you have one value in there at all, you have at least one unique value. And then I used a for loop to loop through the whole iteration with the exception of the last value because essentially you're comparing like I should say the 0 index, the 1 index, and the next iteration, the 1 index and the 2 index, and you keep on marching down all the way to the end, and then eventually you return the result. Mhm. If you could kind of see by my code what I did. So in other words, if the value is on the left is not equal to the right, it's a unique value. Or I should say that the first 0 index versus the 1 index is not equal, then result equals 1 and increment 1 to the right. And if it's the same, then just continue to increment 1 to the right, and left is always going to increment to the right 1. And eventually you get to the end, and it did work.
Okay. Yeah, good stuff. I
It's
like it.
almost exactly how I did it.
I like it. Awesome. Well, let's go ahead and not waste any more time. We are going to go into our next assignment, which is going to be what is going on? Give us a second. A screen have an issue sharing. There we go. We're going to go into our next assessment, which is going to be sliding window pattern. Right, this pattern involves creating a window, which can either be a list or a number from one position to another. Depending on a certain condition, the window either increases or closes. It's a little bit similar to multiple pointers. But it's not. Let's see it at work. Okay. I'm gonna create a list here. One. Something like this. All right. I can't think of a problem that I can use as an example, but I'm gonna talk about the sliding window strategy in a sense. So the way that works is you want to define your quote unquote window, right? And essentially, it's honestly just a sublist, right? The another word for defining what a window is in your sliding window problem is it's really the term sublist, right? Which I'm assuming up to this point in your coding journey, you all know really what a sublist is. For example, this here is the list itself, but I could make a sublist out of these three integers here, right? This could essentially be a list of numbers, right? A sublist within here, right? So a small chunk of the list itself, right? Like a piece of it, that can be considered like a sublist, right? And that's what we refer to when we say sliding window or just window in general, is we're just creating some form of a sublist, right? And I guess the best way of explaining this would be a very simple way of doing it is like finding the greatest sum of three numbers, right? So what you can do is three consecutive numbers, right? Let's make it even simpler. Three consecutive numbers. It's a very simple example, right? We're going to find the greatest sum of three consecutive numbers. So to create your window, you're going to want to start from the beginning, obviously, right? So you would say window is equal to, and let's give this a variable name. Num is equal to. You will start your window, and your window should be the first three numbers within your list, right? Because obviously you want to start either the beginning or the end, but essentially cover every single thing. So you would say something like nums is equal to at the start and up to index 3, which will return to the 1, the 5, and the 2, right? It'll grab these numbers right here. Right. This slicing of nums to index 3 will return to you these two windows, or these three numbers. This will be your window, right? This is that sublist that you created, that window. And then what you'll do is you can probably like add up everything within this list and get the sum and then save it on the side. And once you check that, what you do is with that window created, right, that holds the first three, what you'll do is you'll drop one number, right, the one on the far left of this sublist, and you would add, I hate these things, the next one. All right, so you drop one, but you add the next index that exists in nums. Right, so you shift the window, hence the name sliding window, right? You shift the window by dropping one index and adding the next index. You get the new sum for this and see if it's greater than the previous sum you had. And you do this all the way until you reach the end. right? Finding the greatest sum of 3 consecutive numbers. Make sense? Something like this. That's essentially in the concept of a sliding window. Now, let's look at the assignment. We are doing the sliding window assignment. Let's look at the README. We're going to write a function called max sublist sum. Oh, of course. My bad. I pretty much already explained this problem. Which accepts a list of positive integers and a number called num. So notice here, the parameters, there's 2 parameters being passed in here. The first one is a list, and the second one is an integer, right? The function should calculate the maximum sum of n consecutive elements in the list. That n is that argument num that's being passed in. 2, 4, 1, 4, and 4. So what this is saying is, here's my list. And here is how big of or how many consecutive numbers I should be adding up. Consecutive elements. So there should be 2. It's pretty much giving you the size of what your window should be. 2 numbers. Right? And find the maximum sum of n consecutive elements in the list. Right? So with that logic and what I just explained to you, give this bad boy a try. We'll take 15 minutes on this one. Time is 6:02. Let's go ahead and come back at 6:17. Let's get it.
Okay. So define the function, feed it the parameters. If the length of the list that it sends is less than the number minus 1, then it can't do any of these calculations, and I just have it return none. If number equals 1, then the highest number in the list is just going to be the maximum in that list, so I did that for that case. Otherwise, my start index is 0, and my end index is the number, how long the little sub window needs to be, and my total is 0. While my end index is less than the length of the past list, then I create a sublist starting at start index and ending at end index. If the total sum of those is greater than my total, which started out as 0, then replace the total with that sum and increment both +1 to shift the window over, and then repeat. At the end, return the total. And it works.
Right on. Okay. Pretty cool. How was the algorithm?
It's fine.
Right, not bad.
I thought I had finished a few minutes earlier, but I realized my third case had failed because I didn't account for it being one long. It failed it, so I had to account for that in the
The
code.
edge cases.
Yep.
That'll typically get you. Okay. Right on. Let's go ahead and close the door on this lesson. Let me go share my screen. You have a good example and a not so good example if you guys want to go back and look at the slides of different ways of doing it. The last thing that we have here on the slides is the divide and conquer pattern, but we don't have one for this one, I believe. Let me just correct myself because I've made a habit by accident of just going past things. Okay, yeah, we don't have one in this lesson, but it will be in the next one. Right, divide and conquer pattern. This pattern involves dividing a data set into smaller chunks and then repeating a process with a subset of data. Right, this pattern can tremendously decrease time complexity. Several searching algorithms can fall within this category. Think back to the explanation of log event. This is essentially kind of how it's doing it in a sense. This is more commonly done with recursion, so which is why it's not on this lesson of 11, but it will be on the next one. Just know that there is a divide and conquer pattern, which we will talk about. All right, that concludes Big O and common problem solving patterns. We're going to start searching, sorting, and recursion. This is our second to last lesson for FOP. I'm going to jump straight into it. The first pattern we're talking about is going to be searching a list. Right, searching a list for a particular item is very common. You've seen this in most of your challenges. The simplest one, which is what we're going to be focusing on today, is going to be a linear search. Linear search. Linear search, as the name implies, especially with time complexity, is O of n. Right? O of n. It grows linearly with the amount of inputs, right? Which is n. So here we have a function where it takes in a list and a target. And it's as simple as going for I in range, then looping through the list, and just comparing if something's there, right? And then return it. Well, we can increase the effectiveness of something like linear search using binary search, right? So searching through a list, the efficiency is going to depend on the amount of steps it has to take. If there's 100 items within your list that you have to loop through, worst case scenario is it's going to take you 100 iterations until you find your answer, right? So there has to be a better way of doing it, of increasing the time complexity, or I guess decreasing. Is that the proper wording of it? Or improving the time complexity of your algorithm, right? Maybe looping through the entirety of the list is not absolutely helpful. And that's where binary search is going to come in. A more efficient algorithm for searching a list. Now, I'm pretty sure I brought this up when I first talked about this, when I was showing you guys the example of log of n. It only works if it is sorted, right? When it's not sorted, then the concept of it kind of falls apart. Binary search is part of the divide and conquer pattern we discussed last class, which I had already discussed previously on a different video, which is why we didn't go over it 10 minutes ago. But we're essentially breaking up a data structure in half and then dividing the tasks depending on where it's at, right? Now, Kenny did it. I don't think he was present for it, so I'll just do a small demo real quick, right? Essentially, if you have a list, right, and if you use a linear search, right, which as we saw was going from left to right, linearly from start to end, this notation for time complexity will come out to O of n. N being the number of inputs in our list, right? If there's 8 different elements in our list, worst case scenario is going to take us 8 iterations until we find what we're looking for, right? So this will end up coming out to, worst case scenario, 8 steps, something like that. I think it's 8 or 7. I want to say 7 because of the index, right? 1, 2, 3, 4, 5, 6, 7, 8. I'm dumb. English is hard, and so is math. But we have that. Now, how can we decrease this, Kenny? Well, what we're going to increase or talk about is going to be divide and conquer, right? Where the time complexity of this is O log, I want to say O log of n, something like that. I think that's how you type it in. And what this states, the way that this works is that instead of searching through every single item within this list, what we are going to do is we're going to do a divide and conquer method. So, for example, if we are looking for 8, where's 8? Well, when we did the linear search, we had to loop through 8 different times to find it in this sorted list, right? How can we make this more efficient? Well, what we do is we divide our list in half, right? Where we have left is equal to, let's say, nums up to index 4 or something like that, right? And then right is equal to nums 3 and onwards, 0, 1, 2, 3. No, this should be 4 onwards. Right? We break this up into halves. And then the number we're looking for, we'll check the last index of whatever is on the left side. So we're essentially going to check, hey, is the number we're looking for 8 greater or less than the last index on the left? If it's greater, Kenny, what that tells me is that the biggest number on the left side was significantly smaller. So anything to the left of that is going to be even smaller. Therefore, my 8 can't be on the left. So that means it probably has to be somewhere here. So I'm able to eliminate half of this list in one step. And now I change whatever my left and my right are by splitting the original right in half, resetting the left to be this one here, and the right will now be this one. And then once again, I'm going to use my number that I'm looking for. I'm going to compare the indices for the ending of these. Is the ending of the left greater or less than? What's going to be less than? So I'm able to eliminate this left side. And then I focus on this one here, where I cut it in half and I choose left or right. It's obviously going to be greater than 7, so I eliminate this. And it leaves me with 1 left, which is 8. So what took me 8 steps now took me 3 by dividing it in half over and over again. Right? And that's the divide and conquer method. So how do we do that in code? We saw it already. Once again, let me copy and paste this. Well, what we're going to do is we're going to do a left, which will be something like, we saw earlier, nums up to index 3. Right is equal to nums for index right. But what we also need is a middle. Right? We need to be able to, or what we're going to do is going to reuse the middle and compare that. Actually, I think all we need is a middle. Stand by on this. I don't remember how I do this. I want to say we want to get middle, which will be the length of nums divided by 2. So if this is 8 divided by 2 will give me 4. So 0, 1, 2, 3, 4. It'll probably give me the middle being 5. So this might come down to 5. And what I'll say is 8 greater or less than 5.
Isn't this floor division? So let's just say it was an odd number, would it round down?
Correct. This is floor division. Yes.
Okay.
This will round down. Thank you for pointing out, Jason. Yeah, so what happens here is I get the left and I get the right. And then I also get the middle, which gives me the middle index of my entire list. Using that index, I'm going to grab the... Actually, this returns 4, right? 8 divided by 2 is 4. What's index 4? 0, 1, 2, 3, 4. It returns to me the number 5, which is at index 4. So let's not get that confused. Right? I use the item that's at index 4, which returns a 5. And then I compare it. Is 8 greater than middle? If so, then that means everything that I assign into the left variable is now irrelevant. So what's going to happen is I now need to set a new left, a new right, and a new middle. So I no longer need this. I'm gonna get the right. I'm gonna reassign whatever my middle is by saying something like this. Middle is equal to right divided by 2. Right? Because this is gonna have a new list. This should have a new list. When I sliced it, what this returned was this. Right? So I'm able to grab what's saved into the right, which is a sliced version of my original list. I divide it in half, right? And it'll give me my middle one, which more than likely will probably come down to this. It'll probably give me 6 or something like that. And then with my new rights, I will reassign whatever left is. Right? I'll reassign it. I'll say like left is equal to right, and then pass in maybe middle as the index, because middle is now half of whatever this is. So you use these variables to update what is no longer needed. If left was cut out, then you should update left to represent what the new slicing of the original list should be. And you keep doing that over and over again until you get what you're looking for. Make sense? Let's give it an honest try. Actually, time is 6:32. Let's go ahead and take a 10-minute break and come back at 6:42. I'll see you guys in.
So it's like I kind of get it, but I don't.
That's fair. We should be looking at the binary search. Put these up. Pull some other ones. All right. Let's copy and paste this. And I'm gonna define this function that's called binary search. And as we see here, we take in a list and a value. So I'll say sort list, comma, num. This sort list is the list that we're supposed to be going through. And num is the value that we're trying to look for within this list, right? And this is a sorted list, guys, right? And what needs to come out of here is it should return the index at which the value exists. Otherwise, return -1. So what needs to come out is going to be an integer type, right? Sort list is going to be a list, and num is some form of integer that we're taking in. All right, well, let's talk about this. Well, we need to split this up, right, using the divide and conquer method. So we need to be able to figure out the left side, the right side, and also figure out the middle, right? So what we're going to do is we'll say something like this, where I'll say left is equal to 0. I'll say right is equal to the length of sort list. And what this is going to do for me is I'm going to be able to add these numbers up, divide it by 2, and figure out where the middle of my list is. So this should work all within a while loop. So we'll say while left is less than or equal to right. And maybe I can try it out afterwards to make it seem a little bit simpler. But what essentially should happen is we're going to be shortening the distance or closing the distance between our left and our right pointer, right, as we remove parts of our code.
Wouldn't
Right?
so wouldn't right be len sort list -1 then? I mean, if you're going to go through the whole thing. I mean, if you're pointing to the index at the very right, it'd be len sort list -1. You know,
Maybe.
you start at 0 on the left, so right would be the length -1, the length of the
If
list -1.
if he uses less than in the formula, then it won't matter.
Okay,
Hmm.
or less, while left is less than right.
Yeah, less
Okay.
than or equal to will cause problems if
Yeah,
he's
yeah, but less
using.
than while left and right, I guess in len and sort list would be fine.
Yeah.
less than or equal to right. And do the rest.
Yeah, because I'm just thinking 'cause the length of sort list on its own would be out of range.
Yeah, thank you for that. You're absolutely right. I I always get these confused, man. Just looking at the less than equal signs and the minus, it can get very confusing. Think of that.
Yeah, I kind of got to where like, if the target was the middle, it was good, but then at that point is where I froze.
Okay. Yeah. So let's see it. Well, every time I loop through, I'm gonna grab the current middle. As I mentioned, the middle is gonna be left plus right divided by 2. Right? And this is going to calculate the middle index. And then I'm going to say if sort list mid is equal to num, right? If it's equal to num, that means I've encountered what I'm looking for and I can return mid, right? Because mid is the index, right? So I can just return mid. I don't need to do anything crazy. That's what we have to do. We either return the index at which the value exists, otherwise return -1. But if right off the bat, it's like the middle number that I'm looking for and it's assigned to it, then I found it, right? So I'm just gonna go ahead and return it. If or elif, right? Sort list mid is less than value, then what needs to happen? Or I guess num. What do we call it? We call it num.
Yeah, then you need to check the right side.
If it's less than num, right, then that means that everything in the left side is no longer needed, right? So we need to update the left. So as of right now, left is 0 the first time it goes. So it should be left is equal to whatever mid is plus 1, right? Because we've already checked for the whatever mid is currently located at. So we'll just increase it by 1. But if it's neither of these, if it's not equal to, if it's not less than, then what needs to happen is we need to update right to be equal to what mid is -1, right? And then finally, at some point, what's going to happen as we're shifting the left and the right, at some point, this will happen, right? Where the condition is no longer met. So what that happens is return -1. If we made it to a point where left and right intersect, that means we have not been able to find our value and we should return -1. What lesson is this? Lesson 12. CD, is it 12? No, 13. Python 216 -1. Is that what it is? 216 -1. So, does everyone understand how that worked?
Yeah, I was not going about it that way at all. I understand completely what you did, and it made sense. I just massively overcomplicated it.
That's okay. We have 1, 2, 3, 4, 5, 6. We say that left is equal to 0. Jason, do you understand it, or am I just like wasting my time here?
No, I get it. Like I say, I got up to like where if sort list mid equaled num, return mid, and that's where I just kind of didn't really know how to
Okay,
proceed.
so I don't need to do this. We're good then?
Yeah, I'll probably work through it a few more times just to kind of solidify it in my head later.
All right, just in case. I'm still doing it anyways. Right is equal to
Yeah.
Length
Kenny wants to see
of
it.
list. Okay. So what we do is we created our pointers, right? We did left and right. It starts at 1 and at 6. But essentially, it is 0, 1, 2, 3, 4, 5. This is index 5, right? And as we already know, this is index 0. Well, that's where it starts. When we start this while loop, we're saying, hey, while left is less than or equal to right. So as long as these left is less than or equal to, then we'll keep running this loop. If at any point right crosses over, then we stop that loop because that means we've already checked. We've gone past through here, right? So we started like this, and then we set the mid. Mid is equal to left plus right divided by 2. Well, left plus right now gives you 5. Divided by 2 gives you 2.5, but we did the floor, so it goes down to 2. So mid is 2, right? What is index 2? 0, 1, 2. It returns to you 3. So mid in this first iteration is equal to 3. And then we see, hey, if list index, what am I doing? Oh, I'm wrong. Let me trace back a little bit. When I added left and right and divided by 2 and I floored it, it returned to me 2, right? So mid is equal to 2. We then use that as the index within sort list, right? And compare it to the value. Well, let's say it's 3 and we're looking for 6, right? We compare whatever returns from using index 2 of sort list, which will return 5, to the value that we're looking for, which is 6. Do they equal to each other or not? Well, they don't. Is it less than num? It is. It actually is less than num. So that means everything from mid and to the left is absolutely useless. Right? Absolutely useless. Because we met this condition right here, where if the item in index mid is it less than the value that we're looking for, which in this scenario is 6. If so, then we need to update whatever left is. Update left, which will be what mid is plus 1. Well, what is mid right now? Well, mid is 2 plus 1, which is 3. Right? So left will now end up being 3. But what's pointing at index 3? Right here. What's that index 3? Well, it's 4. Right? We successfully removed everything that was at mid and to the left, and now we are only working with 4 through 5 through 6. And we once again check it. Right? We grab mid. Well, what is mid going to be? Well, it's going to be the 5, obviously. Right? When we divide it, and it's coming down to 5. Is the item at mid less than or equal to the value that we're looking for, which is 6? What's less than? So we need to update left to be whatever mid is plus 1, right? So we remove 5 and 4 out of the equation completely, which ends up just leaving us with one number behind, right? And that's how it's done. Make sense? All right. Let's go ahead and continue. Hopefully that helps. That was binary search. Sorry, my spouse is messaging me. They can't live without us. What can I say? Right? What is big O of binary search? Big O of binary search is a log of n. O log of n. It is better than O of n. It's not as good as O of 1, but it is between them. So we talked about searching. Now, what about sorting? All right, sorting list is another very common computational task. You've seen this. I'm pretty sure if you've done any kind of leak code problems or any kind of coding challenges, you've probably got any question that asks you to sort some type of list. Now, there are multiple ways of sorting, different types of algorithms. And here's a small little table that you guys can look at if you find it interesting that tells you the time complexity of different versions of this algorithm and space complexity. Right? The best possible scenario for every single one of these algorithms. Notice that none of these get anything better than O of n. There's not a single one here that's constant. Right? Not a single one. So keep that in mind. Even the best version of an algorithm, right? There's nothing that's constant. Because that's just sorting lists, right? At least these specific algorithms. I don't know if there's any more. But these specific ones, the best version, time complexity wise, is O of n from what it looks like. And it goes from average to worst. And then we have space complexity, which that one's a lot simpler. But we are not going to go through all these. What we are going to focus on is going to be bubble sort, which is the easiest one. Very common. We're going to do bubble sort as our algorithm. Right? Bubble sort has a time complexity of O of n, with the best possibility being O of n. And I say that because there's different ways of how you can do bubble sort as well. And not every single way that you do will always result the same way. We will not learn all these sorting algorithms because that's beyond the scope of this class. But we will learn a very popular one called bubble sorts. And I'll put a quick pause because my wife is calling me. I do apologize for that. Give me 5 minutes. I'm so sorry. Sorry for that. I do apologize. You know, this families.
Yeah, no, it's all good.
All right, let's go ahead and continue. So we were talking about bubble sort. There's two ways to swap values, which we're going to talk about. Whichever way you use is going to be up to you. There is a method of creating a temporary value, which some people like more. And you can see that here on the right side. Actually, before I even continue, let's talk about what exactly is bubble sorts, right? So we can understand why we are talking about swapping values. Well, here is going to be my list. This is a sorting algorithm. So what that tells you is that more likely the values in this list are not in order, right? This is an unordered list. There's no specific trend here. But the way that we're going to do this is we want to be able to sort the list in the most effective manner possible. There's different ways of doing it, but the method that we're approaching here is going to be the bubble method, right? And the way that it works is think about kind of like hot air rising, right? Or bubbles, right? I like to think of it as hot air rising, right? Because hot air tends to rise while lower air stays lower. Is that correct? Am I correct? All right, good. Science is hard. But from what I'm tracking, hot air rises. Bubbles, it's called bubble sort because of the way it's supposed to bubble to the top. Very similar to like when you're boiling a water in a pan, right? Hot air rises, therefore causing bubbles, making the bubbles come up, float to the top. And the way that it works is it's going to start by taking the very first item, right? And then it's going to grab this item and it's going to compare it to the value in front of it. It's going to say, hey, is 5 greater than 2? And if it is, it's going to swap these. It's going to swap these two together. It'll move 2 to the left and move 5 to the right. And then go to the next one. Is 5 greater than 8? right? And it's going to be false. So it won't be swapped. The next part will be is 5 greater than 1, which will be true. So it's going to swap these two together. So 5 will take the spot, 1 will take here. Then we do the comparison. Is 5 greater than 6? It is not. Is 5 greater than 3? It is. So these two will swap. Right? And that concludes one iteration. After that iteration is going to restart. Is 2 greater than 1? True. It is greater. So 2 and 1 will switch. Is 2 greater than 8? No. Is 2 greater than 3? No. Is 2 greater than 6? No, and so on and so forth. That was the second iterations. Right? And then it goes on to the next one. Is 8 greater than 3? And I want you to notice this. Is after every iteration, at least one number has been formatted where it should be. Right? We're here at 8. It checks is 8 greater than 3, and it's true. 3 takes that spot. 8 takes that one. It compares 8 and 6, which is correct. We want to switch them. And then 6 and 5. Or 8 and 5, my apologies. Then it goes to 6. And it sorts it. Then it gets here, and it doesn't sort anything. And that's done. And I believe that was like 3 or 4 iterations. My bad. I kind of lost track of this part. 3 iterations, 4 iterations. So it took 4 complete loops through here to sort everything. Right? But do you see how that worked? It went for the start. It compared which value was greater than the other. And depending on which one was greater, it swaps them. So then comes, well, how do we swap? Well, there's 2 methods of doing it. One is you create a temporary value, right? For example, here we have a list. We have index 1 and index 2, right? We want to switch index 1, or I guess the value that's index 1. I want to switch it with a value in index 2. Well, how do I do that? We create a temporary value where we save the first item in index 1. We then update the actual value in index 1 with the value of the items in index 2. Then we update the value of index 2 with the temporary value that was holding index 1. Therefore, doing a 1-for-1 swap. This is one way of doing it. Another way of doing it is what my method that I prefer is you call the 2 values that you're trying to swap. Notice that we have the value of index 1 and the value of index 2 separated by a comma. We then say equal, and it's pretty much the same thing, but they're switched. Therefore, reassigning them at the exact same time on one line. All right, so however you swap them is going to be up to you. But essentially, this is how you're going to be swapping using your bubble sort iteration. Make sense? Bubble sort pseudocode. So here we have a little guide of like exactly what it should look like, right? You want to iterate from the back of the list towards the front. Iterate from the back of the list towards the front, right? You're going to start an inner loop with a variable named J from the beginning. And why do we want to start from the back of the list? Let's change a little bit. Let's go with 6, 8, 4, 7, 2. When it first starts, we're going to start the for loop, but we're going to start from the end. And it's maybe it's a little misleading, but the range should be decreasing as time goes on. Because what happens is when we compare 6 and 8, 6 and 8 won't switch. 8 and 6 to 4. Or am I thinking about this wrong? Give me a second. If I switch 8 and 4, this could be 4. This is 8, 8, 7, 8, 2. And then it's 4, 6, 7, 6, 6, 7. Wait, just 2. Okay. I'm a little rusty. We'll see in a bit. The pseudo goal here is to iterate from the back of the list towards the front. Start an inner loop with a variable named j from the beginning until I minus 1. Well, what does that mean? Let's kind of try to draw it out here. Close up binary search, open up bubble sorts. Essentially, we should start a for loop with I for I in range. And we want to start from the back of the list towards the front. So how will we get the back of the list?
List index -1.
List index -1. I don't remember exactly. I mean, the start -1. The stop
0.
will be 0. And then we want to subtract by -1. Something like that. Let's try this. Nums equal to 1, 2, 3, 4, 5. Print nums I.
I feel kind of confused because I feel like the student practice slide seems to be starting from the front, but yet the slides talk about starting from the back.
What are you talking
Or
about?
so the current slide you have on says start from the back, but then the next slide, slide 14, it has you starting from the front, looks like.
This is the swapping. Okay. There's 2 loops, right? You have your loop that controls how many iterations you have to do, and there's the inner loop that does the swapping. That's why it looks like that. Stand by. Let me make sure we're on the right track here. CD bubble sorts. Why are you not printing out? Hello.
Because you're not using indexes, you're just using the -1, 0 going down by 1, which it'll never do.
Nums. Let's go with. So I should be into nums. Are you referring to this?
Yeah.
And I don't think we have.
You
Did we
could just
want
do
to?
should you just do the range, the length of the thing, and then run through it backwards?
Yeah, because I don't think. List index out of range. Oh, let's.
Then num has -1.
Length, it needs to be
So
arranged.
it'd be len nums minus one. I mean, if that's where you're
Then
starting from the back.
I don't think so. Why am I getting so confused? I'm gonna start from the back.
Should be
So
len nums minus one.
you said -1?
Yeah.
Why?
Because the length would be five, but you want for example, you want the four index.
5, 4, 3, 2, 1.
Yeah,
We
that should
don't
work.
we don't want -1. If it's not giving me one though. Is it because up to but not including? Maybe -1 here. There we go. That's why. Okay, just make sure you put -1 here because the 0 won't give you that. I don't know why I had the hardest time with that. But here we're looping through it backwards. So that's pseudocode for that. We want to start an inner loop with a variable named j from the beginning. So that's where we say for j in range of 0 until I minus 1. I see why. Okay, I see why. Yeah, so you want to start a for loop uh to iterate the outside version of the for loop. And then you start an inner for loop to actually do the swapping. But notice that every time that we do this inner for loop, we're subtracting 1 for the original of what I is. Therefore, every single time we loop through, it's doing less swapping because it's taking into account that every iteration you've formatted one number in its correct spots. Therefore, it shouldn't require you to loop through the entirety of the list. And then you compare using the j and the j with +1 and the regular j and swap the values and return this for a list. Okay, yeah, it makes sense now. It's a little intimidating at first, but give it a try. You need one outer loop for overall iteration of what I say iteration, tracking total iterations according to list size. And then the inner for loop does swapping between values. So one controls the overall pace of the iterations, while the inner one is doing the swapping, doing the comparisons. Try it out. This is a little bit more complex. So I'll tell you what, time is 6:28. Take 10 minutes. We'll come back at 6:38. And when you come back, give it 20 minutes on this assignment. So essentially, come back at 6:58. I'm sorry, 7:58. My apologies. Does that make sense? 20 minutes. See you guys then.
Okay. So started out defining it, taking the unsorted list. I decided to keep track of the swaps, but you didn't have to do that. Started a for loop with an I energy, an integer ranging from 0 to the length of the list -1. Started a j, which was I plus 1. Did a while loop, said while j is less than the length of the list, so that it wouldn't just keep going on forever with j. If list item index I is greater than list item index j, so the one immediately in front of it, then swap the two, and I did it the way you showed us, and then increase the swaps. Not really necessary. Otherwise, increase j by 1, and then it redoes the loop again and sorts all of the values slowly, and then run it. There it is.
Right on.
Mine was a little different.
This is the first class that finishes that assignment so quick.
I
Everyone
mean,
always
I essentially use temporary variables. So like if like list of J, or I should say the zero index, was greater than the list of J1, I would use temp variables. And I kept swapping that way. I kept using that to swap them out. I mean
okay.
through the iteration, but it still worked.
You explaining multiple methods on how to swap them really sped that up, because otherwise I would have gone through a bunch of temp variables and it probably would have taken a lot longer.
All right. Okay. Yeah, that was good. That's probably the fastest I've seen someone do it, and I've given them the explanation of temp variables too. But even then, it took a long time. You probably already caught on that you could probably see the examples in the slides if you wanted to cheat, but I'm glad you guys haven't. We went over bubble sort. There is bubble sort count.py. We're not gonna do it because it is the exact same thing as bubble sort, but all you're doing is keeping a variable and keeping track of how many times you swap something. So it's a waste of our time. If you want to try it again, by all means. But I think it'd be better if we just go into recursion already for the last hour that we have. Who here has heard of recursion?
I hate the concept of recursion. It confuses me to no end.
Me too. Absolutely. I hate talking about it. I hate every time we get to it. I
Yeah,
confuse myself.
but it doesn't really it doesn't really make sense to me. I mean,
Okay.
and Guillermo, I think, prefaced saying he doesn't, it's good to just know about it, but you don't really do it that often. So, and it's not that efficient anyway. So,
I don't think it's that efficient. I don't think I have never had to use recursion. I hate recursion so much. I have a friend. I got other friends. My friend groups are all in technology. Like my high school friends, they're software engineers or in cybersecurity. We have a group chat. We talk about coding stuff. Um, I every time that we talk about a coding problem, I ask them, about the problem itself, and it never fails. I have one friend. We'll call him Chris. Every single time that Chris takes a problem, he always tries to find a method of solving it with recursion. Does not matter what kind of problem it is. He will spend 30 to 40 minutes working on his solution just to realize that he overcomplicates it by using recursion and then quits trying the recursion approach and it just goes to do something simple like, actually using loops and dictionaries and whatever. But everyone, like, you don't need recursion to do something. Sometimes recursion, as elegant as it might look, just overcomplicates it and makes it more difficult than it has to be, and you'll waste more time. Right? And as you'll come to realize that not many people are good with recursion. So if you try to implement recursion in code, and there's other people in your team that, are silently not good at it, aka me, then you realize like maybe it's not the best thing to do in day-to-day code. Because it just confuses everybody. Just make it simple. Make it simple, nice and clean, and efficient. That's it. Recursion, it looks cool, but that's all I think it is. I just think it looks cool. That's it. It can be more confusing than it has to be. But let's go ahead and talk about it. All right, we know that functions can call other functions. But did you know that a function can also call itself? This is known as recursion. Um, it turns out that anything you do with loops, you can also do with recursion. There's two constants that you need to know when it comes to recursion. The first one is the base case, right? The base case is where the recursive function stops, right? Almost like a conditional statement, right? Where you're going to continue running this recursive call until you reach the base case, right? Like a while loop, like, hey, while nums is greater than 0, print out, nums. And it'll be like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then reach 0 and stops, right? Very similar to that. Recursion works the same way. It needs the base case or kind of a conditional statement or something that allows the recursion call to stop. Sometimes you can have more than one base case. We'll be focusing on nothing but very simple recursion problems here, so we'll just have one base case. The other element is the recursive call itself, right? Where the function calls itself within it, right? And the way for this to work is whenever you call it again, you have to be able to have something different. Because what's the point of running a function that's going to run the function the same way, not changing it, right? Kind of like running it, once again, a while loop, where you set a condition that, hey, while nums is greater than 0, print out nums. But at no point do you decrease the value of nums. It's useless, right? It just keeps running this while loop and never stops. Same concept. So with that in mind, let's look at it. I don't like this problem just yet. Okay, let's not do that. Before we move on, let's draw it out. So I'm gonna give you a much simpler example. We'll say countdown, right? Countdown takes a number. And we'll say if num is equal to 0, return 0. Else, count down num minus 1. Something like this. So what's happening here? Well, when you run this function, let's say you have the number 3 or 5. We'll do the 5, right? You're gonna run this function, it passes 5, it's gonna check what num is, right? The first time you run this function, it's gonna open up what we call the function call, right? And the way that we like to think about it, it's almost like pancakes, right? Pancakes. When this runs this function, this first call is going to look like this: countdown 5, and it opens up a queue, right? Think of like the queue of the line at the bank or at a roller coaster, right? Someone gets right in line, first person line. That's the first person in queue, right? That person is, in this analogy, our function call. The first time we run this, the initial time that we run this function, that starts the function call. It runs countdown 5. It gets in here. It checks what num is. And it's going to fail the base case. This here is the base case, right? Where we compare num to 0. And it's going to fail. It's not going to pass this check. Therefore, it's going to go into the recursive call instead. So because it didn't meet the conditions of the base case, it goes to the else statement, which in turn calls countdown again. So what happens to this function? Well, it never finishes. It stays open, right? And as a matter of fact, it dives deeper into itself and it calls a function again, but within a function, right? It makes another function call. But this time, the num passed in, we subtract it by 1. So it ends up being 4. Right? This function runs. It checks what number is num, which is 4, equal to 0? No. So it fails the base case. It goes to the else statement, and now it reaches another function call. Because we didn't meet the base case, we then again call another function of countdown. So it opens up another function call. At this point, and none of the 2 previous functions that have been called have closed. They are still open. They are pending tickets. Right? Think of like, I need to go to the grocery store to buy groceries, but I can't go to the grocery store because first I need to fix my tire because my tire's flat. But I can't fix my tire because I don't have the tools. I'm missing a tool, a jack, right? I'm missing a jack, so I can't fix my tires because I can't jack my car. Well, therefore, I put my initial task, which is go to the grocery store, on hold. I still haven't completed it. It's on hold. Because I have another task, which is now fixing my tire, but I can't fix my tire because I'm missing my tool. So now I have to find my tool, right? So like it opens up different tasks, and the tasks aren't completed. You're diving deeper into more tasks that need to be completed. Now I have to find my tool, so then in turn, I can go repair my tire. I gotta repair my tire so I can then go and get groceries. Make sense? That's kind of what's happening here. We're opening up tasks or things are added to the queue that can't be closed out or completed until the most recent task has been done. So countdown 4 gets ran and it runs countdown 3. And it does this over and over again because it keeps failing the base case. This time it's 2. This time it's 1. And finally, it gets to a point where it runs this function and num is equal to 0. So this specific function call here, it's the 1, 2, 3, 4, 5, the 6th function call it took. It opened up 2 function calls. It finally meets the base case, and it says that this is 0. So therefore, instead of running another function call, this returns. This is going to return zero back to the function that called it, and this closes out. Right? And it goes back into whoever initially called the function. Well, countdown of 1 was the function that called countdown of 0. So 0 returns here. Right? And because it returns 0, it gets to this one. And what this happens to do is, how can we do this?
It's like an avalanche. It just keeps returning 0 and closing down the one before it, right?
Yeah, but not what I was trying to get. Let's go with return num. Is this the way of doing it? We could do return num, which is 0 there. Um, return 1. How AI supposed to do this? Give me a second. Oh, I think I missed something. We can do print num. Instead of returning something, maybe we just return. Or I guess we can return 0. Print num. And just return. Okay. How about this? I think this one looks better. When it gets here, num is equal to 0. It's going to print 0. Right? I guess this will make more sense if this function was count up, maybe, or count down. One of these, it would make more sense, right? But when it gets here, it's going to print out 0, and then it's going to return in here, which then in turn closes out the function call, which printed out. Oh, okay. I see what it was doing now. Let's remove this. No, this actually is good. Okay, let's talk about order of sequence. I'm sorry if I'm confusing you guys. Here, sequence. The first time we run this, it fails the base case, but it prints out num. So it prints out 5, right? And then it opens up the function call. It goes to count up 4. It gets the else statement, prints out 4. It goes into count on 3, prints out 3, opens up the next function call. And it does that until it gets to 0. And we have to put print here because when it gets to countdown 0, it doesn't go to the else statement. So we have to print it there and return. So it will return anything, but in turn, it was able to count down anyways as we open up this function calls. But finally, this all ends up returning back to the start, right? Because this returns, then this one returns, and then this one returns over and over again. They're not returning anything in this situation, but they finally closed out once it reached the base case. So I was able to print out my sequence of numbers to count down from num to 0. And then once I reached that base case, which is arriving to 0, we closed everything out. Didn't return anything. That's okay. Because the task at hand was to count down to begin with. And I was able to achieve that every time that I opened up a new function call. Right? So it opens up, it prints out 5, which ends up also opening up another function call, goes to countdown 4. It prints out 4, opens up the next function call with 3. It gets the else statement, prints 3, so on and so forth. Eventually, it gets to countdown 0. It prints out 0, returns, and it starts closing them out. Make sense? And turn give you the result to appear that you're counting down from whatever num is down to 0. Does this make sense? Or no?
It does. I just don't understand why you wouldn't use a basic loop.
Right? Absolutely. Yes.
Now, if you were doing something like manipulating a list and feeding that into the recursive method or function, like let's say you had a list that had 8 elements. It was 8 elements deep, so 0 to 7, or yeah, 0 to 7, and you start a recursive function, you feed it that list, and it says like while the length of that list is greater than 4, uh, or if it's equal to 4, then return, else feed that list again, sliced down one element to the next one. Would that work in recursion? Because it doesn't work in normal for loops because you're modifying the indices and you're calling those indices. Do you understand what I'm trying to say?
Yes. I think it would work. Yes.
Because if you do it in the for loop, then it'll go out of range quickly because you're still calling the same original number of indices, but then you're cutting it down, so you're quickly running out of range. But if you do it in recursion, then it's calling a new length every time until it reaches its endpoint, and then it can return.
I think that would work. Yes. I know exactly what you're talking about. Well, like I said, recursion just overcomplicates things. You could achieve the same thing with loops. There's no specific reason, which is why I mentioned from the start, like I'm not a big fan of recursion. It can overcomplicate this. Even something as simple as counting down, as you saw how complicated it got. I even had to kind of like take a step back and make sure I re-explained it. So I was, achieving the effect that I was trying to portray to you guys. I even had to reformat my function to ensure I conveyed my message effectively. But it significantly overcomplicates it. You can achieve the same result with a for loop. I completely agree. Uh, the main reason why we do this is to show you that you can do it. Not necessarily that you should be doing it, but that you can do it. It's there. It's present. Some people like to do it. Some people are good at it. Here's one way of doing it. If you want to add this to your tool belt, you definitely can. But I will say you probably won't ever really have to do this. So uh, take that as you want. But it's still my job to teach you that this is a thing. Make sense? All right. So we talked about the recursion call. We have an example here, which is the factorial. What happens here is we get a number and we compare it. We set up the base case, which is if num is equal to 0, then we return 1. If not, what happens is we take that num and multiply it by what's supposed to be the return call, or the recursive call, right? But notice that we're also changing the num as we progress. And we can see how this works. Let me see if I can open up. I guess I can open recursion intro. Yes, sir. Recursion intro. Okay. We see this in real time. And we'll say factorial num. If num is equal to 0, return 1, else return num times factorial num minus 1. And I'm missing this here. Let's see how this looks like. Factorial of 12. And I got to print this out. Oh, way too big. Let's lower this to 5. There we go. So the factorial of 5 ends up being 120. We can try to print out num. What does it look like? Print num. Let's see if I get it visually to show us. So it starts as 5. And what essentially happens is it multiplies 5 times 4 times 3 times 2 times 1, right? 5 times 4, if I'm correct, is what happened. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120, right? So the way that factorial works is that they get a number and they multiply it by the number that comes before it. And they multiply that by the number that comes before that, and so on and so forth, right? That's how that works. And recursion is a great way of doing it because you're able to do it just like this, where you're able to take in that num and then multiply by what's supposed to be the return of the following version of you calling this function. So this is a great way of when you can use recursion to solve an issue, but this is a very situational time where recursion will work very well. and this is the most common one that you'll probably see, is either the factorial version or you'll see the Fibonacci sequence is another one that's pretty common for recursion. But we set up the base case, we set to 0, and then return 1 at the very end. Right, this is that 1. Else print num, which is what we end up doing. Let me get rid of this. But the very last function call that gets called ends up returning 1. This is that 1. Right? It ends up taking that spot which is being multiplied by num and the previous function call that called it, which ends up being 2. Right? So you see how this is working? The very last one that gets called is 1. Well, the function that called it, num was 2 at that time, right? Because the one that called that very last function, it decreased num by 1, therefore reaching that base case. So every time as we nest our way back up from the call stack, we know that we are multiplying the previous result of the next level of our call stack being incremented by 1, therefore reaching this effect of 1 times 2 times 3 times 4 times 5, right? Because that's what we started with, the 5. I don't know why it's like this. Recursion example, a better version of doing it. All they're doing here is removing the else statement. Essentially, I mean, it's correct, right? If it doesn't pass this code snippet, it's automatically going to not run anything else except the next line, right? Which would be 4. So it's a little redundant to add else here because it's still going to run the whatever is supposed to be in the else statement side, right? Kenny said, if you ever watch Inception, it really helps to understand recursion. Yes, I usually I bring that up whenever I get to this slide. Absolutely. Recursion is literally Inception, right? Nesting yourself into, deeper versions of the same dream or somebody's dream of a dream, right? Something like that. That's kind of what recursion is doing. You're just diving deeper into a different version of the same problem. And that's going to be the recursion intro. .py, which is what I was using to code in, but the README should be here. You'll see that one of these problems is probably the same one I did, but you're going to write the following 3 functions in the recursion intro.py file. The first problem is going to be write a recursive function called countdown that takes a positive integer parameter and returns a string that counts down from that number to 1. For example, if 5 is passed to the function, at the very end, you should return this string. Notice, this is a conjoined string. It's not you printing out every single time you run to the function. At the very end, this needs to return one string, which is the equivalent of all the numbers conjoined together. You can use string concatenation in your recursive function to build up the return value. You can do something very similar on the next problem, but this time you're going to count up. And then third, you're going to get the sum of all the integers from 1 to the number that's being passed in as an argument. All 3 of these is being done recursively. We're going to take about 20 minutes on this because it can get very confusing. You might want to break your head with this. So we'll come back at 8:40. At 8:40, we'll take volunteers, 1 for each of these, and then we'll call it a day. I'll see you guys at 8:40.
I'm not allowed to get rid of that.
All right. So write a recursive function called countdown. Let me put this over here. And let's remove this. Define countdown. That takes in a positive integer, right? And returns a string that counts down from that number to 1. So returns a string. Well, the example here is 5. If 5 is passed to the function, it should return the string 5, 4, 3, 2, 1. Well, my initial function that I need to run needs to return this string completely. How can I achieve this string by the end of my recursive calls? Well, at one point, if I'm starting at 5, at one point I need to come down to 1. So I should say something like if num is equal to I say greater or equal to, no, less than or equal to 1, we can say, or 0, I guess. No, we can say 1. Return 1. Else, what I need to do is I need to return a string. Well, how is this string going to look like? Well, I'm currently at the very top, right? The very first recursion call. What is num right now?
5.
5. So I probably want to ensure that whatever I return back is num plus a space plus countdown with num minus 1. Something like this. We can actually delete this. It should look something very similar to this, right? Where I get 5, I join it together with a string, or I guess we can just do this. I don't know how it's gonna look like. I'll do this. Num space countdown. There we go. Something like this. So what is gonna happen is my final product is gonna have 5. It's gonna be a string. It's gonna return a string with 5 being here, a space, and then something's gonna take the place of here. Well, the next time this calls, num is gonna equal to 4, right? So it'll become 4, and then become 3, then become 2, and then become 1. So when it becomes 1, this will return, take the place of this spot. Within that function call, if this is going to be 1, the current function that's on, num is equal to 2, right? And it's going to keep returning these and returning and conjoining my strings together. Now, if I did this correctly, I should be able to print countdown and 5. Let's see. And there you have it. We have 5, 4, 3, 2, 1. As a matter of fact, let's print num. Every time, right before we call the recursive call, I'm going to print what num is. Right, the first time it runs, it's 5. And then we put it in a string, right? And we decrease num by 1. So every time this function call opens up, num is a different value, and we're just joining all these strings back over and over and over again. Make sense, Tim?
It does.
If it doesn't, let me know. I can break it down even further.
No, it does. I was returning string str parentheses num and then comma calling the function again, which is why I was returning a list or tuple or something. I don't know. I was getting the countdown, but it was surrounded in parentheses separated by a comma, so it wasn't quite there. But I understand what you did.
Okay, bet. Well, let's do count up. Define count up. And once again, we're going to take in num, which is going to be a string. And this should return a string. I'm sorry, not a string. It's going to be an integer. Right? Now, we'll say, how can we do this? Mm, I want to count up, right function, count up that takes a positive integer parameter and returns a string that counts up from 1 to that number. Okay. If bias passes that function, it should return the string 1, 2, 3, 4, 5. You can string. Okay. I'm gonna go ahead and I'm gonna pass in a variable called start, and I'm gonna assign it the variable of 1. I'm sorry, the value of 1. This is what I'm gonna use to start this count up. Um, I want to say something like, how can we do this? If start is equal to num, right? So we can start at 1 and we're gonna increase this. Very similar to how like we were decreasing for the base case until we reach like a certain value. We can do something like that. If start is equal to num, then I want to return, I guess num, right? Return num. Else, what should happen is I should return start, and count up. With num, or I guess I would increase start plus 1, right? Let's try it. Let's see how this works. Print count up. Ah, no. Okay. Um, we are increasing count up though. Oh, we're not passing in num. Num needs to stay the same, but we need to increase start by 1. Let's see if that works. There you go. Okay, that was the issue. Let me remove the other print statement. Okay, so very similar to the countdown, I just switched the logic a little bit, right? On countdown, we were starting with a bigger number and we didn't bring it down. Therefore, all we had to just make sure it was greater than 1, right? That's easy. We can hard code that in there. But num on count up it's different, right? Num can be anything. It could be 5, it could be 10, it could be 15. So I can't necessarily uh if I want to count up, I need to start from 1 and then go up to num, right? So how can I get that? Well, I can create a default value, which is start, assign it to 1, right? And that start was what I used to start the bottom part of this string, right? As you saw here, the first one is run, it's going to add 1, right? The first function call that calls it will be 1. So what's on the far left is 1. And then I'm going to join it by whatever happens the second time I call this function again, which in that time, start increases by 2. So therefore, what's being added here is 2. I got an issue because I didn't pass in num, right? And num is an argument that this function needs to be taken, right? Num, all I'm using num for is to keep track of when my count up, my start variable, finally reaches it, right? So that's the only reason why I need it there. But once I finally increase start to the point where it matches num, then I just return num at the end of it, which is 5, right? That should be the final part of the count up. Therefore, returning 1, 2, 3, 4, 5. Make sense?
Is there is I mean I guess you could probably, I guess the thing that complicates this is the string, inclusion. So would there be a way to do it without having to have throw a start variable in there? But, I mean, if we weren't having to convert it to a string.
Uh I don't. Yes, I think.
Yeah, it's just because the problem itself doesn't, just talks about throwing in the
Sure.
one integer,
Let's try this.
but we're kind of throwing start in there, just to make it easier for ourselves.
Okay, fair
Right.
enough. We can probably say something like if num is less than or equal to 1, return 1. I think so. Hold on. Else return. What I'm gonna do here differently is I'm gonna add yeah boy. I'm gonna add num on the right side, right? Because it's starting at 5. And then I'm gonna put count up on the left. And here I'm gonna subtract it by 1. Let's see how this looks like. I might do some. Oh, there you go. Yeah. Bada bing, bada boom. You just switched it on the string of how you're conjoining them together. Does that help?
Yeah.
So now you have 2 ways of doing it. Okay. Um, did anyone finish the third one that they want to show? All right, not everyone jump at once. All right, let's do the third one. For this one, we write a recursive function called sum count up defined sum count up that takes an integer num int parameter and returns the sum of all the integers for one set number. Okay.
And it'd be essentially the same as count whatever direction, except instead of adding as a string, you're just adding some count up to
Pretty much,
what you
right?
had before, to the number that you pushed originally.
Yeah. So we can say if num is less than or equal to 0, then we want to return 0. But if not, what needs to happen is we're going to do num plus
Count up
what
num plus one,
some come out. Yep. Some count up and minus 1
minus one. Yeah.
or num minus 1. Um, it sounds like you're getting it now, Tim. So that's good. We'll use the example here of 5. And if we run this, we should get 15. There you go. Pretty straightforward. All right.
Yeah. What kind of clicked for me was I realized that when I call it, I'm just looking for the previous iteration, the value to be what that call is going to be.
Yeah, the last one was the easiest one. It was the string part that was making it shitty. Or sorry, I should have said that. This,
It's okay. It happens.
the string, concatenation section that was making 1 and 2 hard, but 3 was actually very straightforward considering I already did factorial.
Yeah, the string. I mean, I'm not gonna lie to you. The first time I picked this one up, I was like, "What the heck am I doing? Like, what's going on?" So yeah, it did throw me off the first time I saw it too, and that's okay. Uh, but hopefully this gives you some kind of idea about recursion. We talked about the call stack. Oh, we didn't talk about the call stack. So when running a recursive function, multiple copies of that function will be active at once. That's one thing to take into mind. But only the most recent one will be executing. The others are essentially paused, right, while waiting for a result. going back to the analogy I talked to you guys about, where like, when you have like a chore to do, but that chore is dependent on something else, and that's dependent on something else, so you can't complete any of them until you get to like the very last call stack, and then you handle it in that manner. And that's kind of how that works, that call stack. We have more recursive stuff, which we'll do tomorrow. Times is 8:53, so let me go ahead and stop the recording.